Hi everyone, welcome to video number 2 for Module 7 on moderated and nonlinear models. In the previous video, we were discussing moderated models in which we have interactions in greater detail. And in this module, we're going to be talking about nonlinear models, where we actually have curvilinear functions or even potentially nonlinear functions that we're trying to model in our regression framework. So again, as a reminder, when we're talking about these two different types of models, when we have a moderated model, we're saying that the effect of one variable changes as a function of another variable. So we had this little like thumbnail of a graph as a bit of a guideline, right? Where if we have two different groups, the slope of one group is going to be statistically different from the slope of the other group. Or when in the example that we worked through, when we were looking at the interaction of two continuous variables, we said that your baseline VO2 max had a significant influence on how much your VO2 max decreased when we took you up to altitude. And importantly, that the effect of that altitude changed based on what your baseline VO2 max was. So people who had higher baseline fitness actually showed a greater decrease when taken up to the same altitude. In a nonlinear model, it's something that's a little bit similar, but actually quite different. So in these nonlinear models, we're saying that the effect of a single variable changes as a function of itself. So in the moderated case, the effect of x changes as a function of some other variable. In the nonlinear case, we're saying that the effect of x changes depending on where exactly along the x-axis you are. So in this little thumbnail, you can see if we go from -1 to 0, right, we don't actually change the value of y all that much. Whereas if we go from 0 to 1, the value of y changes significantly. And if we were to go from 1 to 2, the value of y would change even more. So in a nonlinear function, a 1-point change in x doesn't guarantee the nice linear change in y. So when we're talking about nonlinear models, this actually comprises a very wide category of models. And this includes what I would say are more correctly called curvilinear models and truly nonlinear models. So what do I mean by that? Well, a curvilinear model produces a curve, but the difference between a curvilinear model and a nonlinear model is that a curvilinear model is linear in its parameters, but it might have some nonlinear variables, right? So it's linear in its parameters. All of these are just beta 0 plus beta 1 times x plus beta 2 times x plus beta 3 times x. But I can actually get this combination of linear parameters to produce a curve if the variables that I'm feeding into it are nonlinear. So for instance, I can have maybe a variable that's age, then I would have age squared, and then age cubed. And this would ultimately produce a cubic curve, even though I'm adding together linear slopes, right? Because the x variables themselves don't linearly change, but the betas themselves linearly change. So this is what I would say is more correctly described as a curvilinear model. But it could also cover truly nonlinear models in which we have different functions, for instance, an exponential function like the one showed here, or a logarithmic function, or a power law function. Those would all be nonlinear models because they aren't linear in their parameters. They actually obey different rules. They aren't just linear combinations of variables. So that's a bit of an esoteric point. We're going to focus most all of our attention on curvilinear models because these actually have a lot of power, and we can estimate them very easily using our general linear modeling framework. Because again, these are linear in their parameters, and we know how to make linear fits of parameters based on different x variables. So we can feed information like this into the same least squares estimation system that we've been using throughout the course in order to make appropriate calculations of the reduction in error and appropriate calculations of F statistics and T statistics and etc. So we're going to focus on these curvilinear models to understand how we can actually make curved estimates of the relationships between variables. So again, using the altitude data set that we used in the previous example, we can see how the VO2 max of these 105 athletes changes as a function of the altitude at which their VO2 max was assessed. So we assessed their VO2 max at once at baseline. Then in a hypobaric chamber, we simulated altitude of varying heights. And then we tested their VO2 max again, and we recorded the change in their VO2 max. So for everyone, it was a decrease relative to their baseline assessment, which was conducted at sea level. But you can see that for different people, they fell off to different degrees, and people at higher elevations fell off more. So if we wanted to fit this with a linear model, like we've done before, and we're pretty well equipped to do, we could just say that we have their decrease in VO2 max as a function of an intercept and a slope multiplied by the altitude that we took them to. And this model would be linear, right? Altitude is just altitude in kilometers, and we'd be comparing it to a Model C, where we say, well, we're just going to estimate a single constant value. So Model C would estimate the mean decrease for everyone. Model A would estimate the best fitting intercept and slope as a function of altitude. And if you do this in R, this is the output that you get, right? So here's our formula showing the decrease as a function of altitude in kilometers. We get an estimate for the intercept, its standard error, and then a t-value and a p-value for a statistical test. We get an estimate of the altitude, its estimate, standard error, and a t-value and a p-value for a statistical test. Then we get the r-squared statistic and the f statistic testing the model as a whole. And if we were to take this intercept and this slope, right, and plot it over our raw data over here, we get what looks like this dotted red line. So at 0 altitude, right, at sea level, our model would estimate that there's actually a slight increase. You get almost a 1-point bump in your VO2 max. All right, and then it's going to say that the best fitting slope is negative 3.4376. So for every 1 kilometer increase in altitude, we expect that your VO2 max will decrease by an additional 3.4376 points. So if we kind of follow that along here, we don't start quite right at 0 because no one started at 0. No one was retested at 0 kilometers of altitude. But 0 would be somewhere back in here. And by the time we get to 1, that's gone down 3.5 points. We go to 2, that's gone down another 3.5 points. And then when we get to 3, that's gone down about 3.5 points, and 4, and so on. And so for every 1 unit change in X, we see this decrease in Y, starting from the intercept. So hopefully that feels like a bit of a review, right, if we fit a simple linear model to these data. But we can also look at this and say, well, maybe this isn't actually a linear change. Maybe we, in eyeballing this, it looks like, going from 1 to 2 doesn't lead to as much of a fall off as maybe going from 3 to 4, right? The change looks steeper on the right-hand side of our graph relative to the left-hand side of our graph. So maybe these data would actually be better approximated by a curvilinear model. So if I wanted to test a quadratic, right, by including a squared term, all I would need to do is to create a new variable called altitude squared. So I'd have my linear variable, which is altitude, and then I would just have those values squared. So 1 becomes 1, 2 becomes 4, 3 becomes 9, 4 becomes 16, right, and 5 becomes 25. But that is actually a new x variable, which represents altitude in square units. So I can plug that into my model, including this new beta 2. And now if I wanted to compare this model as a whole, right, against Model C, the Model A, Model C for a full model comparison would look like this. I have a model that just estimates the average, right, the best fitting constant value, which would be the average decrease in VO2 max for all people, compared to a model that's going to make a conditional prediction based on the linear change in altitude and on the squared change in altitude. And if I fit that model using R, I get something that looks like this. So here's the formula, right? We're predicting the decrease as a function of altitude in kilometers and altitude in kilometers squared. We're going to get an intercept. We're going to get a slope for the linear change, and we're going to get a slope for the quadratic or the squared change. And you can see here our model estimates that we're going to start at negative 2.2708. So when altitude in kilometers is equal to 0, which means that altitude in kilometers squared is also equal to 0, our estimate is going to start at negative 2.278. And from that negative decrease, we're going to estimate more of a decrease, right, as the altitude increases. And we'll work through some models in just a second to show you the exact predictions in each of those situations. But first, I want to show you the models that we're comparing when we make these statistical assessments. So this is the ultimate output of our model, right? This dashed red line. But how do we make a decision about whether or not the model as a whole is good, or which of these individual parameters we think are really explaining significant variation in our data? Well, in order to make those comparisons, we have to compare different Model A's and Model C's. And as we mentioned before, this F statistic for the model as a whole, with 2 and 102 degrees of freedom, has a Model A that includes all 3 parameters, right, being estimated, to a Model C that includes just 1 parameter, the intercept, right, being estimated. So our intercept only model compared to our model that includes a linear effect and a quadratic effect is not a very good explanation of the data. And in fact, we explained about 65% of the variance by including both the linear and the quadratic term in there. And that is a statistically significant decrease in error, right? Our F statistic, our F observed is quite big. Now, we can write this a little more explicitly, right? Because what we're really saying in this model C is that we're forcing this to be zero. We're saying there's no effect of altitude, so we think there's a non-zero effect in model A. Here we're forcing this again to be zero, so we say there's no effect of altitude squared, and here we're in model A, we're saying there's a non-zero effect of altitude squared. When we test the model as a whole, however, we don't know which of the parameters is really doing the work, so we have to look above and say, okay, which of these parameters is actually providing, explaining most of the variation in our data. And it's also important to remember that these are controlling for the other values, right, that we see. So here we're looking at a model A, model C comparison where we have a model that has beta 1 times altitude and beta 2 times altitude squared being compared to a model C that controls for everything else but forces beta 2 to be zero. So it has a model that has everything in it compared to a model that has everything except altitude squared in it. Similarly, if we want to look at the effect of altitude, we compare a model that has everything in it to a model that has everything except the effect of altitude in it. So this forces altitude to be zero, and by comparing these two models, we can say controlling for the intercept and the quadratic effect is the linear effect of altitude statistically different from zero. And similarly for the intercept, right, that's a model that has everything in it compared to a model that has everything in it except the intercept. So we force that intercept to be zero, and we say, does this model explain the data statistically better than a model that forces the intercept to be zero, controlling for the linear and quadratic effects of altitude? So each of these comparisons comes from the same model A, but a different model C. And we'll always have a model A that has everything compared to a model C that leaves out the effect of interest. And by doing that, we can ask, what's the unique contribution of each of these individual parameters controlling for the other parameters in our model? Okay, so now that we've looked a little bit about where that statistical inference is coming from, how do we actually interpret these parameters? Well, we can take these parameters from our linear modeling output in R and actually write them out as an equation, right? So we have our intercept of negative 2.2708. We have our estimate of beta 1, which is negative 0.6921 times the altitude, right? And altitude's the variable, so we plug in individual values to get our estimates there, minus 0.5432 times altitude squared as a variable, so we get our individual estimates there. And again, this part in red is our model, right? So it's going to generate predictions that would fall perfectly on this dotted red line. Conversely, our actual data points, right, the y sub i's, are the blue dots, and there's going to be a difference between each of the data points and the model, which is going to leave us with the residuals, which I've highlighted here in green, which would be the difference between each blue dot and the red line, right? And if we took the difference between each of these, we could actually calculate each of the residuals, which is something we'll be working on later, and how to work with residuals and actually check the assumptions of our residuals once we've built this model. For now, though, let's take a look at what our model's actually predicting and see if we can make sense of these model predictions. Let's find out, let's solve for the intercept in this situation. Okay, so first we can plug in 0 as a value for altitude, right? And altitude squared then would also be 0 because 0 squared is 0. So this is easy to simplify because this is going to go away and this is going to go away. And we're just going to be left with our intercept of negative 2.2708, which seems to agree with what we've plotted here. Right, at 0, the estimated value of y is going to be negative 2.2708. If we want to now say, well, what is the predicted decrease in VO2 max at different altitudes, we just need to plug those values into our equation. So at 2 kilometers, right, the linear effect, that's altitude in kilometers, so that's 2. Altitude squared is the squared value, right, so 2 squared is 4. So we have negative 2.2708 minus 0.6921 times 2, minus 0.5432 times 4, which ultimately reduces down to negative 5.4678, which we can see agrees with what we've plotted on the line here. At an altitude of 2 kilometers, we've decreased by negative 5.5 or so milliliters per kilogram per minute in the VO2 max. Now we can change this and go to another step further, right? And let's say, well, what happens if we go up to 4, right? So if we go up to 4 kilometers, well, now we're going to plug in 4 for the linear effect of altitude and 16 for the squared effect, the quadratic effect of altitude. And this is ultimately going to lead to negative 12.2904, right? So you can see that lines up nicely with what we have on our prediction line here. At 4 kilometers, we're predicting a decrease of negative 12.2904. And if you plugged in these values for every possible altitude we have in kilometers, what you would find is as we go up, the predicted change from one point to the next is getting bigger, right? At higher altitudes, the cost of going up another meter or another half meter is higher, and our predicted VO2 max is going to fall off more, which you can see, right? If we go from 0 to 1, we haven't changed very much. And if we go from 1 to 2, we haven't changed all that much. We've gone down at about 5.5 milliliters per kilogram per minute, right, from 0 to 2. But now as we go to 4, we don't lose just another 5.5. We actually lose 12.29. Okay, so as we can kind of alternate back and forth between these two, right? You can see as we went from 0 to 2, right, we lost negative 5.5. As we go from 0 to 4, we don't just lose 5.5 again. We actually lose more than that, and we've lost negative 12.29. Okay, so you can see, if that wasn't clear from the curved nature of this line, you can actually just look at the differences between 0 and 1, 1 and 2, 2 and 3, right? And you can see that that effect is getting bigger as we go farther along the x-axis. So there's a nonlinear, or more specifically, a curvilinear effect of altitude in this case, where the effect of altitude on VO2 max is negative, but it's more negative at higher altitudes. And finally, what we would get out of R is an ANOVA table similar to what we've seen before, and we'll do some exercises in lab to work through this, right? But again, even though we have these quadratic and maybe cubic variables in our model, we're still using a linear combination of parameters, so we can explain them very well using our general linear modeling framework, where we take the sum of squared errors by taking the difference between our data and the model's predictions, squaring it, and then adding all of those squared errors together. So we're going to be able to fill in an ANOVA table much like we've seen before, where we get the sum of squared errors for each effect, right? The residual sum of squared errors for our model A, the total sum of squared errors assuming our simplest model C, right, where we're just estimating the average for everybody, and then the degrees of freedom in each of those cases. And then we can calculate the mean squared errors for each of those, and then turn those into ratios of F observed and calculate the p-value associated with each F